Oh, that's fine. Okay. Well, I actually start correcting the title. I'm not the CEO of the company. I'm actually running the U.S. office of CloudMinds. So, but thanks for promoting me. Yeah. Okay. So, well, I was asked to do an introduction of CloudMinds in 5 minutes, right? So I was just asking myself, what would be the best way to introduce a young startup, but yet with a very bold vision? You know, as people say, a picture is worth 1,000 words. And then if I could extrapolate that and say a video is probably worth 1,000 pictures, which you probably just saw already, right? Which is like probably billions of words going on already. What I want to do is I want to start off by showing you guys a very short video. It's about 40 seconds versus 6 minutes earlier, right? I'm hoping to use that video. It's actually a scene from the movie The Matrix. If you guys are, you know, the Matrix fan, you definitely remember this scene. And I'm hoping to
Can you fly
tell
that
a
thing?
story. And then I'll talk about what CloudMinds' bold vision is, because I only have a few minutes, so I'll only stay on a very high level about what our vision is. And then if you guys have time later on, we could chat about the specifics. And then we have people here sitting in the back from CloudMinds, and they will all be happy to answer any questions you have. All right, let's get the video going.
Not yet.
Operator,
Tank, I need a pilot program for a B-212 helicopter. Hurry.
can you fly that thing?
Not yet. Tank, I need a pilot program for a B-212 helicopter. Hurry. Let's go.
I'm sure if you get the first part was actually the most important part, but it just, you know, flew by really, really quickly. But the point is, when, you know, Leo and Trinity, they were fleeing and they ran to the top of the building, right? And they saw this chopper in front of them, but obviously neither one of them could fly it. And that's why asking Trinity, can you fly that thing? And Trinity said, not yet. And then what's happening later is interesting, because then you saw this operator probably sitting somewhere in the cloud with computers, and she, you know, she was then empowered with a pilot capability. And then that's how they, you know, jumped on the chopper and flew away, right? So the takeaway of the story is then, you know, let's fast forward many years. If you look at a robot, the chances are the robot will have a very powerful cloud component to make robots of all kinds to quickly have a capability or a skill or even persona, right? This is a perfect example to tell CloudMinds' bold vision. So with that, let me, I just have a couple of slides actually. Again, I want to go back to the movie scene a little bit more, right? Because if you think about it, for humans, it's going to be very difficult for us to be upgraded, right? How can you upgrade yourself with a meat body? But yet with a robot, that is actually more realistic, right? So that's what this whole movie scene is all about, that you can empower a robot with a new capability in a matter of a few minutes. So I'm using this quote from James Kuffner. I don't know if anybody in the audience know him. He is currently with the Toyota Robotics AI Research Institute, and he was a professor at CMU. Right? So he was the person who coined the terminology cloud robotics. So that I want to give the credit to James Kuffner, and also want to lead into the company, right? So I have one slide that has all the high-level status or data about the company. So as I mentioned earlier, CloudMinds is positioned as a cloud robotics operating company. Again, I want to remind you guys about what's happening in that movie scene, right? So you have a cloud component, and you have to have a network component, and then you have the robot, right? So what CloudMinds is aiming to do is to build up that secure and fast network infrastructure so that it actually can connect the robots of any kind with the cloud brain. Right? We call it Cloud Robotics Engine. And then that completes the picture. Granted, that vision is very bold, and it takes many years to realize. CloudMinds' mission is to take a staged approach from what we have today and to get to that vision. Right? So if you look at this picture at the lower right portion of the slide, again, it tells the three key components that CloudMinds as a company is working on. So we have the cloud platform. It's a combination of cloud AI with what we call a human augmented artificial intelligence. We call it HARI. With that, even before the artificial intelligence reaches to the level of a human intelligence, you can combine the two and then deliver a seamless user experience to the user. And then the robots of all sorts, right? There's even a robot puppy dog, I think. And then there's Pepper, there are other things. There are also IoT devices. To connect the two, as I said earlier, it's critical to have this network that has global coverage, that is fast and secure. Right? Think about, again, the movie scene where, if the linkage between Trinity with the cloud operator is hacked, what's going to happen, right? A lot of terrible things could happen in that scenario. So the secure and fast network that has global coverage is a critical component of our product portfolio. So this is basically what we do on a high level. If you guys are interested in knowing more about what CloudMinds, the product strategy and stuff like that, you're welcome to talk to us at the end of the presentation. And then again, quickly rundown of the company. We actually are fortunate to have the world's leading investors as our seed round investors. We have SoftBank, Walden International, Keystone Ventures, and the Foxconn. As you know, Foxconn and SoftBank, they're very much into robotics, right? They acquired the French company called Aldebaran. And then we have office locations in 3 countries. We have offices here, thanks to Zhongguancun, right? And then we have a large office in China, and then office in Japan as well. So the company was founded about a year and 3 months ago. The founder and CEO, again, going back to the earlier point, is actually Bill Huang. If you guys know Bill, he is a serial entrepreneur, and before starting CloudMinds, he was the head of China Global Research Institute. And then before that, he was a CTO and co-founder of a company called UT Starcom. And then we have about 200 people. We actually got talents from all the top companies in the AI, robotics, and telecommunications industry, right? So with that, I want to conclude this presentation. And then one thing I want to add is that we're very actively hiring and looking for talents. So if you guys are interested, you can either go to our website or you can come and talk to us. Wenbai, myself, and there's some people actually sitting in the audience. We'll be happy to tell you more about what we're looking for. And with that, I think I will hand it back to Wenbai. Hope you guys all enjoyed the presentation today. Thank you.
All right. And so before we start this session, I'd like to thank you all the volunteers. You can see the people behind helping you, registration, bringing the food and so on. So I'd like to thank those people who helped for this event to be successful. Let's give applause. Okay, so now to to our main feature, right? Presentation feature like a movie. Okay, so the speaker is Xiaoping Liu, and he is a Google Brain senior software engineer and also the machine learning researcher. is one of the author of a TensorFlow, and that's what he is going to focus. In his work, Xiaobing focused on application where TensorFlow could be applied in Google product, many of those such as Google Search, Play Recommendation, and Google Translation, and so on. So before Google, Xiaobing was a senior staff engineer in Tencent, leading the development of a large-scale distributed machine learning system, which is widely used inside Tencent. So let's welcome Xiaobing for the talk.
Hello, everyone. Oh, it's good. Hello, everyone. I'm Xiaobing Liu. I'm from Google. and I'm software engineer and working on TensorFlow. Today it's my honor to give a talk about TensorFlow. I'm going to talk about deep learning. It's for everyone. Why I have this title? There are two reasons. First is TensorFlow is open source and is accessible from everyone. If you have interest, you can just download it and play with it. It's pretty easy. Another thing is TensorFlow is designed for deep learning, but with very simple. The concept is a data flow system. So we are going to have TensorFlow very easy to learn, very easy to play with. So that's kind of another perspective why it's for everyone. So here is my outline. First, I'll talk about how deep learning affects Google's products. Many products already using TensorFlow and have planned to switch to TensorFlow. Another is I'll talk about basic idea for TensorFlow. What's Tensor? Why it's flowing? And why it's a data flow system at the workstation, something like that. Then, because TensorFlow is a distributed system and we care a lot about scalability and parallelism. So I'll go to talk about something, how to split model and how to split the data to have good parallelism. Finally, I'll cover something about how in TensorFlow can express those things very easily. And finally, well, I will have some example like LSTM. Why it does not show up? Yeah, LSTM and other topics as well. First of all, this is a very simple example. And you can know that first, don't talk about deep learning, just talk about machine learning and how can we classify those two sets of points. One is the other is the oranges. You can say that we can easily draw a line between them and easily to separate them. So it's a very easy classification problem. And the line is actually y equal W times X plus B. W is what? W is weight and B is bias. So for the machine learning, we need to feed more data like those points, and we need to learn the W and B. And finally, once we get W and B, we are going to use it for real prediction to say which point it belongs to which. Okay. Here for TensorFlow perspective, it's a classification problem. We are going to draw that line. How can we learn that line? So we have because input have two nodes and output have two nodes. One node, so we will have two connections. And those two connections, we will have 4 weights and 2 bias. And so for machine learning, we are going to find the best parameter to perfectly to separate those two set of points. So this is a kind of a little harder problem. How can we classify them? You might know some traditional machine learning algorithm like SVM. SVM is basically do some kernel transformation. Then in some high dimension, these two set of points can be easily classified, just like that previous linear problem. But in deep learning world, we just need to add one hidden layer with 4 neurons. And you can say those two sets of points can be easily classified. And there is an even trigger example. And for this example, we can just add more neurons in the middle hidden layers, and we can get 100% accuracy. You can see that. And here is a real problem, an image, a picture, right? We can say that for human being, we can easily know that it's a cat, not a dog. But how can computer know that? What computer really see is just some pixel, just some float values like 100 by 100 pixel. So we will got 10,000 float value. By this float value, how can computer know this is a cat, not a dog? So we are going to use machine learning or deep learning to solve this problem. And so that's why we need deep learning. Basically, for deep learning, that's because we have multiple neurons, multiple layers. Each layer have multiple neurons, and our layer is deeper and deeper, so we call it deep learning. And from here, we can just get a simple impression that from 2012, first come out deep learning applied on the image domain problem. And from that time on, we got deeper and deeper model. And right now, last year, 2015, the ResNet got 152 layers. And at the beginning, it's just 8 layer or 10 layers, something like that. And also, you can see that the accuracy got better and better. Right now, we got 3.57% the error for the top 5. This is ImageNet. It's a ImageNet classification competition. And you can see that when we got deeper and deeper, we got better and better results. Here is just for a comparison. And we have the a little shadow model, 2012. AlexNet just had 8 layers, but for last year, the ResNet model have 152 layers. And you might know that in the CIFAR, the recent result, we got 1,000 layers to have the best result to solve for ImageNet classification problem. Okay, so we will go into some detail and what kind of problem deep learning can solve. Okay, first of all, it can solve some object detection in the image, right? It can do some image understanding problem. From this pixel, we know it's line. And second, it can do some speech recognition, and it's very traditional task in machine learning. And also, it can do some ranking. You might know that Google has rank brain for deep learning, and you just feed the query and document the pair. And from output, you can get the ranking for the different document. And you know Google search, so this is learning for search problem. And here is the machine translation, and you have one language and translate to another language. And this is the image captioning, just to tell you what's this image includes, and how many objects do it have, and what's the relationship between them. Just to tell you a story about this image. This is evidence why deep learning is widely used in Google. And this is a directory which includes the TensorFlow model pipeline. And you can see that from 2012 to last year, the directory going up and up, around like 3,000 directory possibly. And it's very widely used in Google. Here is some products like Search, Ads, YouTube, and Google Map, and many, many products you can imagine. And why deep learning is so popular in Google? Because basically we treat it as a universal machine learning platform. It's end-to-end. We feed the raw data like we have speech, text, we have entity, we have sparse feature, and we get prediction, we get the classification, we get the sequence result from it, like learning to rank or like whatever. So it can solve many, many problems. So in Google, we treat it as universal machine learning. It's not just like a traditional machine learning system. You have different lot of engineering. But in deep learning world, you don't bother to do that again. So we got some, in deep learning community, we got some very good state-of-art result like speech recognition and image recognition and many of those problems. So you might have an impression that deep learning is might be powerful in Google and possibly in other companies as well. So next step, I'll show you some basic idea, concept about the deep learning and how does it work. First of all, the neural network is a very traditional model like 30 years ago. And it just learn a complicated function between two spaces, first space and the second space, the input space and output space. And like this example, and we have the image like a cat. Then we have multiple layers. Each layer have many neurons. Basically, this is a convolutional neural network. And the final label is cat or dog. Do the classification. Why we can do this? Because basically, you can learn something hierarchically. From bottom layer, we know some very raw feature, and from higher layers, we know more abstract feature like colors, like age, like texture, something like that. Finally, you got to say, okay, this is a cat. And this is one neuron. And in this neuron, we have multiple inputs, x1 to xn. And for each input, we have one connection to the neuron. And each connection has one weight, W1 to Wn. And finally, we got one activation way. And what's the function for this neuron? It's just a weighted sum of all the inputs. And finally, apply the function f. What's f? Currently, the most popular one is a rectified linear function. We call it the ReLU layer because it's very easy to learn, and it does not have some problem like gradient vanishing problem. So ReLU is a very popular activation. And from here, it's very easy, but the thing is you need to use many neurons, many layers to solve a real problem. Here is another example. You know that we want this weight. We learn this weight very well. And basically, we just need to feed more and more input. From each input, we learn something for this weight. Like this. This is just a snapshot of a current step. We have we have 3 numbers. And for next, sorry. This will be have another, okay. Anyway, I'll explain this a little later. It just iterate more and the weight got to be updated. This is learning algorithm, and we have we have data and we have label. This label is a cat or dog because this is a supervised learning problem. And feed the data from layer to up. We got the prediction. Then we compare this prediction with the real label, and we got the either match or miss. If it miss, then we need to update the weight to do a good job next time. So we will backpropagate this loss and update each weight. This is a learning algorithm. I just for loop and pick the training example input and label, run the neural network on the input and adjust weights on the age basically W to make output closer to label. And how we can, because we can get whether it match or have the loss in final prediction, how we can backpropagate this loss into bottom layer. It's called the backpropagation algorithm. And the basic idea is to follow the gradient for each weight. So each weight will be learn better and better. So this is that example, and this is first the one step. And the next step here, we just update each weights. Okay, so here we know something about deep learning or neural network, and we also know Google uses a lot of these things. So next step, also something, what kind of model exactly being used in Google? And this is a very traditional task, speech recognition. And before Google, lots of technical are explored for many years, around 30 years. But for 2012, first try deep learning on the speech recognition, they got 30% word error reduction. So it's a breakthrough for this problem, speech recognition. This is one example. At that time, the deep model is just a very simple feed-forward model, and you just apply the feed-forward model on the acoustic signal, and got a final label. Just train it, and it's a breakthrough at that time. And right now, it's the architecture gets very fussy. You can see that from bottom, there are some convolutional layer, and you just apply on the frequency, just like an image. Then for the second part, we have LSTM layer. Later, I'll talk about LSTM as a very popular model in deep learning world. And finally, we use a fully connected layer to increase the capacity of the model. And this model architecture is exactly being used in Google speech recognition system right now. And from last year to this year, there are other things like LSTM model end-to-end. You just feed the original speech signal, and you get final text image. So because it's so powerful, I incorporate many things into this model, like lexicon and the language model and the acoustic model, and all of them are just one end-to-end model. And that was speech recognition. And next, this is for image part. ImageNet is a very popular competition in art. And basically, you picture and this is some example. And this is a very old architecture. That's the first one on this area. We call it AlexNet. And in that time, just 2 towers, and each tower just has 8 layers. And finally, 2 fully connected layers. And it worked well at that time. Right now, I just that we have 1 layer or 1,000 problem. And this is 2015. Our Google won the first place on that competition. And this is architecture of that model. And this is some example. You can say whatever what kind of meal is basically can be recognized as a meal. And this is snake and dog. So where this technique be applied is used in Google photo search now. And you can say it's original image. You apply the deep convolutional neural network, and you can tell what is. This is other like image search, because right now you can semantically understand this image, so you can search it by text or by the query. Okay, this is combines the vision with the translation together. This is one thing in our Google's mobile as one product. Okay, that one is a convolutional neural network, basically. Next step, I'll talk something about a sequence model. Sequence model is very popular and very powerful today. What's sequence model? Basically, it's a recurrent neural network. It has additional dimension, which is time. With time, you can unroll many times. It can memorize something. Like this is the RNN, because for each hidden layer, we have the one additional connector to itself. So when you do the unroll, because you have, this is the time sequence data. So basically, it will unroll many times from t minus 1 to t and t plus 1. So it's a 3-step. For hidden layer itself, it can memorize the previous state. This is a very powerful architecture for many problems. This is one example for translation. LSTM can be used for translation. The one particular kind of RNN. And for this translation problem, because basically no matter what language you are speaking, basically you have the one shared knowledge between different languages. So this is source language, and we use a deep neural network to translate to some shared knowledge. Then from that knowledge space, we decode to another target language. So this is this is also used in Google and many other companies right now for translation problem. Because traditional translation is just use a phrase or n-gram. You basically count many things by statistically. But right now, it's just end-to-end deep learning to solve this problem. And this is 2014, and our team published one paper. This is a kind of breakthrough on this problem. You can see that state of art is 7 blue point. That is traditional. It already took about 20 years to solve this problem, got 37 blue point. That was the first try on neural translation by using deep learning. 37 at the bit state of art result. Yeah, it was amazing. And here is another example using the sequence model. This is, we call it image captioning. Basically, you need to understand this image and tell a story about this image. The idea is you encode this image by deep neural network into a shared space. And you can just think of it as a vector of high dimensional float vector. Then from that vector, then you decode into a text, the description about this image. And this is the architecture more detailed. And you can say the first part is the convolutional network. You get weight. Then from here, you use LSTM model to unroll many times. For each step, you predict one word. And finally, when you finish unroll, you got one about this image. This is some example. You can say like this one, a group of young people playing a game of frisbee. Yeah. This is another thing we call it word embedding. And word embedding, basically, you want to understand what the text for each word or each sentence. How to train it? It's very easy and very simple. You just pick one word as a label and train it by using multiple hidden layer. And finally, you got a word. You get some distributed like vector representation for this word. This is one thing. After you learn this word and the text, you can say if two words, if they are semantically close to each other, then if you apply this high-dimensional vector into some space, you can say that, like this example, C word and they are at the camera. And this is the rank brain we used in Google Brain for learning to rank. And basically, right now it is the third most important individual signal in Google search. And it works very well, especially on some long tail query. And this is detail about it. And basically, we just feed the query and document pair and use this to do the ranking and scoring. And this is another example for smart reply. Also use the sequence model. And you can say, basically, it will automatically reply for you by reading your email. And two steps. First is whether activate or not. Then after that, use LSTM model to generate reply. It will generate 3 reply candidates. You can just click it, one of them, and do the reply very easy. This is AlphaGo. AlphaGo is a big thing this year in AI area. And there are 2 key points in AlphaGo. First is AlphaGo combines deep learning with reinforcement learning. This is a very powerful model, actually. Another thing is the hardware perspective. AlphaGo is using TPU, that is Google specialized hardware to speed up the deep neural network. So you can see that deep learning is somehow very powerful, can solve lots of problems. And also, deep learning has a few different kinds of models, like I just mentioned, the feed-forward model, convolutional model, and the sequence model. And also, deep learning needs very huge data. So for a machine learning system, how can we solve this problem with high performance and very good scalability? So I want to summarize the requirements of this system. First, it needs to be very easy to express, so very easy to use. You can try lots of ideas and algorithms like deep learning in our reinforcement learning algorithm by using it. Very easy and it's flexible. That's the first thing we care about. The second is scalability, because we have very huge data and we want bigger and bigger models. So scalability is very important for us. And the third, we need portability. And you can run whatever you want platform, like a mobile, like a laptop or desktop or a cluster. And finally, it's very easy to be reproduced. So if we use TensorFlow, I use TensorFlow, we can easily share our research, our idea, because we are in world, basically. So with these requirements, Google Brain implemented a second generation deep learning system called it TensorFlow. And why is the second generation? First generation is actually disbelief, and it's scalable very well and good for production, but not very flexible and a lot of restriction. And so for second generation, TensorFlow solve a lot of those things we care most, and also published and open source it. So you can just download it and combine it with lots of examples. You can just play with it. So here I'm going to talk something about TensorFlow. Why it's called TensorFlow? What's tensor and what does it mean for flow? For the tensor, it's a very basic idea. A tensor is just some data, holds some data like a scalar, just one integer, and all are also our vector, our matrix, our cube, something like that. It's very easy, just a data. And how it can flow, because in TensorFlow, everything is a graph. So here is flow. And the tensor from the source point flow into other parts of just follow this connection. And you can see this is the one example. And yeah, finally we call it up, and we execute it, and then the tensor will flow from up. This is a little bigger. So a practical answer is that is TensorFlow very easy to use, easy to install, maybe in a laptop or in a cluster for distributed training. Yes, it's very easy. I just go through a few steps and install the TensorFlow. This is just the 4th step. You can try it offline, and then finally you will see that we are ready to use TensorFlow. Just a few Python lines and import TensorFlow ITF and create a constant up like hello TensorWorld. just execute it, and you will get hello world, just like C++ or whatever it's to install. For the distributed training, so we need to set up a cluster, and for this cluster, we need to different machine or different process to recognize each other. So from here, we can say we have some classes spec, we have some parameter server, and we have some worker. And later, I will explain detailedly about what's parameter server and what's worker. But right now, for a distributed setup, you basically need to set up a different process, make sure they know each other. And this is the computational graph. You can see that with distributed setup, you have different parameter server, and you have two sets of weights. Well, weight equal to weight 1 bias 1 and weight 2 bias 2. They are in two different parameter server. And for each worker, it just do something very simple, just do matmore, relu, plus bias, and finally you got your loss. And so next step, you just for loop the train, run the train up once many times until the model converge. This is more detailed to explain this. This is very, it's called TensorBoard. It's a good tool to visualize the for you. And so you can just say what graph looks like for your model, and a lot of nodes and a lot of connection, and you can add too big to see the details about your operation. And this is another tool, we call it timeline for the performance analysis. Here, from bottom, you can see that there are many different color of box, and each operation, or we call it op, and how long times it takes to finish this execution. So for different layer, you can see a lot of parallelism in this. And from here, you can see this is just one GPU. And you know we have multi-thread, so also the good parallelism in there, even in just one GPU. And this is a TensorFlow software stack. And from bottom, it's just a different hardware, like a GPU, CPU, Android, or iOS, and is TensorFlow execution system. Finally, you just need to build this graph. How can you build this graph? You can either use C++ front end or Python front end to build this graph. Once you have this graph, you just need to execute it with a session to drive it, and so you finally get what you want. So this is a graph, and fundamentally it's just a data flow graph. And this graph, we have some nodes. We call it a tensor. As you know, tensor is without any state, and with a connection to some operation. And the operation will basically implement the same. For this example, just x plus b. Tensor without any state. And also we have some special tensor. It's called a variable. Variable is some we need to fetch. We keep this state and update this state. Finally, we have this state as a parameter for us to do some real prediction. So one thing is for TensorFlow, since it's a unified graph, and no matter what kind of model, how complicated it is, it's just a graph. So this graph can be across many different devices, right? Like a multi-machine, multi-GPU, or we have lots of like machine in one cluster. So since it's a unified graph, so how this graph can cross many devices. So conceptually, it's very easy. whenever you want to cross one device, you just add additional 2 nodes, send and receive nodes, like this. From device B to device A, you add additional 2 nodes, send and receive. So it's connected. So in this case, we can just fetch mathematics. We want to know the result from mathematics from the final result. It will automatically transfer tensor from different devices. This is other connection between them. And this is a unified graph. Do you need to execute the whole graph when you execute something? No, you just need to execute the subgraph of it. Basically, you will the feed node, we call it the input or feed node with B, and output something like F. We want the first result from F node. So it will just execute this subgraph instead of a whole graph. It's basically very easy for idea for the graph partition. So what kind of training algorithm TensorFlow has? We have 2 different algorithms. First, we call the asynchronous training. Another is the synchronous training. They are just a different version. I will explain a little. So for this async training, and basically we have multiple workers, and all the workers, they are just independent, and they get the parameter P from the parameter server, because parameter server are shared between different workers. So you just get the latest P and do the computation and compute loss and gradient for all the P, then back the delta P for, back to parameter server. You can imagine this way they are more efficient and more robust. If one worker crashes, the other worker just continue going forward without any wait for this case. This is another, we call it synchronous variance. And for this variant, our worker just get one copy of P and aggregate the result, then update the delta P back to parameter server. And you can see from this diagram, it's we have the more big effective batch size. So in some cases, you need to tune the learning rate for it to have a good model quality. Another thing is it may slow down by some worker, so it's not very good for the fault tolerance problem. But in some cases, especially like ImageNet, if we do synchronous training, we basically got a very good result with faster converge speed. And also we see this improvement in other model like a language model. So I just mentioned that we will apply the delta P back to parameter server. So basically, how can we apply back? We have different optimizer, different algorithm. First is stochastic gradient descent, SGD, is very simple. You might know that. Another thing, the second one is momentum, and to try to solve some problem of SGD. And also we need to adaptive learning rate for different feature. We might want different learning rate. So that's ADA-GRAD. And also the same thing for ADA data and ADAM. They have some difference in some cases, but conceptually they are same. Just want to use different learning rate for different feature. And finally, too, they are proximal ADA-GRAD FTR proximal because they have L1 and L2 regularization for this. So basically, you can use this algorithm to solve the overfit problem for your model. So scalability and parallelism is very important for us, for TensorFlow, to be as a good distributed training system. So what kind of parallelism we have? First is the model parallelism. You can just think of, if you have a very big model, you just split it across many machines. We call it a parameter server. then you can make your model bigger and bigger. Just one thing, have more machine for it. That's it. So it's have good scalability. Also, data parallelism is we have huge data. So we have many workers. Each worker just consumes some part of data. So if you have more data, you just increase more worker for it. And for the concurrent step, it just means every node in this graph or every operation, we don't have. So whenever you and without any deadlock or data races on it. Finally, it's some single operation because it's a C++ kernel, and in that kernel you can use multi-thread to speed up. And this is some practical concern for the training speed. Normally, if you train your model just in minutes, then you can interactively do some research. If you train model just 1 to 4 days, then maybe it's fine. But 1 to 4 weeks, then we just to consider some very high value experiments. But if it takes 1 month, then yeah, don't touch about it. It's too slow. You cannot do any experiment on it. So training speed is a big thing, right? So how TensorFlow can do this thing at a good scale, and how TensorFlow can make distributed training very easy. So this is the first thing about model parallelism. We just partition the model into different devices. Like this example, we have 2 hidden layers, and below is the input image, raw image, and we can split by horizontal or by the vertical, whatever you want. And normally, because convolutional network has some good property, it's called the local receptive field. So if you partition it by the vertical, almost you have some good performance like this. And for the data parallelism, it's very cheap to get, right? You just need more worker. And there are some number for this kind of density, normally 10 speed up if you use a kind of 50 replica or 50 workers. Some sparse model, normally you can use 1,000 replica, so you can get more speed up on it. This is diagram for the data parallelism. We will go it step by step. So we have a few different workers. We call it a replica. Also, we have the shared parameter server. So the first step, we get is a parameter from PS. Then we, based on the local, we do the computer loss at the gradient. Delta P is the gradient. Then we update back. And then we get P prime. And this is second step. We just get P prime and update it back. Again, it's very easy. And all the work in these things independently. Basically, this is asynchronous training. Or another option is synchronous training. And you will get n times larger batch size. The good things, no gradient staleness, but bad things, it's very hard to get easy the fault tolerance for it. This is some success of the data parallelism in Google. And for RecBrain, we use 500 replica. At ImageNet, we use 50 GPU, and normally we can get 40x speed up compared with the CPU or single replica. Also, there are some other examples like Smile Reply as the language model. Basically, we just need more replica. It's a natural idea. And this graph shows that when we have the data parallelism, normally we can get like 35 speed up for this example, because for 1 GPU, you will get 80 hours to converge 1 point, 1 accuracy. But if you use the 50 GPU, you just need no more than 3 hours. So this is some example I just showed. Next step, I also explain something about TensorFlow execution engine and how TensorFlow set up, because it's a graph, how this graph can be executed. We have some options like this. This is just one machine. You can set it, you can use it in a laptop. In this case, we have one client and one master and just one worker. With one worker, you might have some multiple GPU. And for this case, we just run the session. And for this session, it will drive the graph to execute. And remember that when you execute a graph, you will feed an input. And then you fetch one up from that graph. So it will just run the subgraph of that. This is a kind of distributed version. And in this case, different worker will do some graph partition. So each of them just runs subgraph in the whole graph. And between the master and the worker, it communicates as a gRPC, which Google already open sourced. This is a very popular setup for us. Normally, if you have multiple workers and multiple parameter server, then each worker has one trainer. And this trainer will drive the worker to execute this graph. And they just do it independently if it's asynchronous training. And in this case, I treat it as a model parallelism, the different worker as data parallelism. So the whole system has good scalability. In this distributed setup, how can we make sure it has fault tolerance? Then that means if some machine crashed, then we recover the. Let's say this is different worker, different parameter server. Then we have another job like a visualizer to show the whole graph of your model and then help you do some performance tuning. And in this case, if the parameter server crash, each worker will know that our variable are not complete. Some part of it move forward. Worker will restart, and our parameter server restart. Once they restart, they just load the previous checkpoint. They keep saving some checkpoint onto the. So you just load the previous checkpoint and the from point moving forward. And in this, if the worker crash, the thing would happen because it's independent and just wait that worker restart and recover. If the trainer crash, then trainer will just restart. All this setup, all these things will management by the Kubernetes, which things already open source by Google. So basically, you can use the Kubernetes to management all your jobs in this distributed setup. So basically, it will has good fault tolerance for this system. So next step, another TensorFlow, because we have good parallelism in TensorFlow. We can easily express those things into TensorFlow into some language like C++ or Python. This is one example. I'll talk about LSTM. LSTM is a very popular one. As in each box, and there are many different operations. And basically, we call it IJFO. And each gate will have the 2 matmore. And each matmore will take 1 take H and 1 take input. Basically, if you get I and J, you will apply some activation. 3 of them apply sigmoid, and 1 of them apply tanh. Finally, they will get new C and new H. You can see that diagram in this picture. And in TensorFlow world, just a few lines of code to express all those things. You can see that we have the split. We split the state from H and C, the previous state. Then we do the linear mathematics, do the linear operation. It includes all the mathematics inside of it. Finally, once we got the result, we do a split into 4 gates. And then we do some activation and linear operation between them. Finally, we got a new M and a new C. So this is just one step of the LSTM. Before I going forward, I'll explain a little about the sequence model for different kinds of domain. One is translation. Here you can see that we have some source sentence, we have the target sentence, and we want to translate between them. Here the thing, we basically, this is called the encoder decoder framework, and from the encoder, we encode the source sentence into some intermediate representation, which could be called sort vector from Geoffrey Hinton. When the encoder sees the mark end of sentence, then the decoder began to work and translate from the shared sort vector into a target sentence. And basically, you do the predict step by step. For each step, predict 1 word, like this. And for the accuracy perspective, for the decoder part, actually we do the beam search. And if you know something about beam search, then it will just keep all the possible top hypotheses for each word. And finally, you get overall best score for all the sentence. You just pick the best one. Okay, for a real translation model, I'm talking about Google translation system. And another big thing is the attention algorithm mechanism. And here you can see in this diagram, we have encoder and we have decoder. In the middle, we have attention part. This is very important because with attention, it can help the long sentence keep information, go through the LSTM model until the encoder part. For the encoder part, you can say we have a sentence. We have I enjoy it dot. For each word, we will do embedding lookup, represent it with a high-dimensional float vector. After that vector, we have multiple LSTM layer. For from the horizontal part, I enjoy it basically unroll different parts. So you can remember LSTM, we have the H, we have C. For each box, we will output a new H and a new C. And once we got new H and a new C, we will feed into the vertical and the horizontal. And vertical, we just increase the capacity of the whole model. And we will get some dense representation. With those things, you feed into an attention mechanism. And with this attention connected to decoder part. So just with float vector, for each step, we'll decode 1 word from it, like this D1, D2, D3, D4. This is pretty much similar what we are doing here in Google. And this is another example for sequence modeling. Okay. Hi. Stopped. Oh, okay. Okay. This is image captioning. Yeah, I mentioned this architecture before, so I just skip it. This is my reply. Same thing for the sequence model. and you feed the source sentence, which is just the email content, and you will get the reply automatically generated. And here is the Tensor code line for this LSTM. And basically, because LSTM, we need to unroll many steps. Like this, we just unroll 20 steps. And for each step, we have the XI, like a sentence, I enjoy it. So, and also we have H and C, or we call it M and C. It's same thing, previous M and previous C. Then after the LSTM cell, just one box, remember that there are 8 some activation function on it. Finally, we will get one pair M and C. We just unroll it next step. So this is just one layer. And if we want to increase model capacity, we want to deeper and deeper, right? So we are going to use four LSTM layers. So this is another for loop. For this for loop, then we just replace some variable like it's. So basically you will unroll horizontal, and by the vertical part you need to go through the out layer or LSTM layer. So this is basically you use this code to graph for the TensorFlow. So for TensorFlow part, we need to run it distributed. Okay, we do it. Suppose we want to run it in multi-GPU, and here is saying we want each layer run in different GPU. Then you just insert one additional line. pf.device, we have GPU 0, 1, 3, of them corresponding to each LSTM layer. And here is the example, and we can also know that TensorFlow will actually run all these. This is first step. We have A fit. We have source sentence. This is the first word. And we feed into the GPU 1. And once finish, it will have a new M and a new C. Horizontal LSTM and vertical part. And for the vertical part, actually is GPU 2, and it will, the TensorFlow will flow to that GPU. And this is third step. The 3 GPU are running in parallel. And this is fourth step, 4 GPU. And here is same thing. And for the decoder part, also pretty much similar as the encoder. And you see one step by one step. Finally, for the softmax, because for a real translation model, we use the softmax, and we predict the possible target word. That space is very huge, like we have 80K target vocabulary. So it's very huge, and we have very huge MetaMod in it. In this case, we can still split multiple GPU, so they also can run in parallel. So this is a single machine setup for all the things. And you can say we construct LSTM model with batch size equal to 16 and hidden layer units equal to 200. Then you just execute it to many steps. And if we want to run it in distributed setup, then just we have some red line insert. And first of all, we have replica device setter. And the one argument to tell you how many parameter server you want to use. And after that, you a supervisor. Supervisor, one special worker called the chief worker. So chief worker is responsible to do some additional things. First is initialize all the variable and report some summary like AOC loss, log loss, or something you care about. Also, the chief worker will reload the checkpoint and save the checkpoint into the disk. And once you have supervisor, you just need to create a session. Once you have session, you just drive the graph to run it step by step until the model converged. So yeah, this all things about TensorFlow, that scalability and parallelism and how TensorFlow can express those things very easily in Python code. And next thing, I will talk about some trick to train a good model with TensorFlow. Possibly before that, you guys have some questions discuss? Sure, go ahead.
Thanks. I've been dying to ask this question. Can the cluster be spread across data centers using Kubernetes or other technology, or does the cluster have to be in a single physical data center?
It can be a different data center. But normally we don't set up like that because there's some communication overhead.
Sure, you're going to have latency, but
yes,
if you already have an architecture that has data parallelism spread across the globe,
yes,
then
they still need to talk to each other, right? Transfer the parameter between them. So if you cross the data cluster, it will pretty slow for that. So,
but time may not be the issue in this case. It may be the data has to live in the region where it is.
Yes.
Right.
Yes.
So there's those political issues.
Yeah, for data that's the same. But another thing, the parameter you try to put a parameter with the worker together. That may be a good setup. But conceptually, TensorFlow support that, and Kubernetes support that.
Thank you.
Question?
Yeah, sure.
Yeah, I was wondering, Google Translation sometimes asks feedback to see if the translation is good or bad. So how does our input affecting the future translation?
Sorry, you mean the translation neural network, right?
Some translation ask to see if this is good or bad. If it is not good enough, they ask for feedback. So my question is, how does our feedback affecting the future translation result?
I think that's a good question. Actually, we are trying to create some new algorithm. Basically, it's more like a reinforcement learning. And if a user gives some feedback like or don't like this translation result, we will give a reward or penalty into our current translation system. So it's more like a reinforcement learning for this. But yeah, currently it's not in the production yet. It's still in the research stage.
I have a quick question. On the parallelism slides, can you show that one? The previous slide. The one before it. The previous.
Okay.
Yes, this one.
Yeah.
So the GPU one needs input A to execute, right?
Yes.
But at that time, your GPU 4 hasn't given the output A yet. How do you parallelize?
In the first step, only GPU is running, just idle.
Yes.
Yeah. In this example, it is, but in real, in the real system, no step, right? So in that case, the GPU is just running on the previous example.
Right, but on the sixth step, your GPU 1 needs an input A, right? From the GPU 5 or 6. But at that time, the GPU 5 and 6, they haven't got the result from GPU 4 yet.
Yes.
How do you...
They have to wait until
then this parallelism just stored, right?
Don't know why it's working. For this example, you can see that step by step, and only until all the input data are available, then
yes.
that GPU is right?
Yes. So it's not really easy to pipeline this, right?
Okay. I discussed it offline. Okay, if no question, I will quickly go through my left slides. Okay, there's some trick to train a good model. First one is the state delay time. And what does that mean? Because distributed training, you don't want our one software to set up simultaneously. At the same time, you want them begin to run gradually. So you just set a time like 15 seconds for normally get better model quality on it. Second trick is the parameter sharding strategy. You don't want too widely or too narrow to partition all those parameters into PS. So normally need to do some to best setting. And for the big batch style, you need to tune the learning rate, as I mentioned. And finally, you overlap the communication and the computation. I will have an example to show that. And other normal trick, just a gradient cell, you just drop it and some clipping and okay. Okay, there are other trick like embedding regularization, and you just use the FTR or process graph, something like that. And because we are using ReLU layer, all the use this times the sparse speed training. And the third trick is for communication. Basically, we don't need any flow communication between them. Waste resource, and we can convert. And after the get result, use it and do some fusion if possible. And try some single replica work first, and then try multiple replica. And gradient checker is good. And finally, you can try over drop out. 16-bit communication. And basically, before the send and the receive node, we will have two conversion nodes from float to FP16 and from FP16 to float. So you will save half bandwidth. Why we can do that? Because normally for float we have 8-bit exponent at 23 Matisa bit, and we can just truncate it into 16-bit, and do not have any accuracy hurt. Send and receive node, we have the specific implementation for different device, like a GPU between GPU or between CPU or different machine, either RDMA or gRPC. This is one example. You overlap the computation and the communication. Instead of assume we have multiple layers, and we can get all the parameters over first, then run all the hidden layers. But we don't, because in that case, stack by the communication. For a better one, you can overlap. You can get the for the first, then just once you do the computation for the second layer, same second parameter for the second layer, and for third and the fourth layer. This is some simple trick. Normally, you can speed up training speed or to train a good model. And finally, the thing I want to mention about enhance existing machine learning system. Normally, TensorFlow is a general framework, and it's good for deep learning, but it does not mean the only for deep learning. You can try lots of things about traditional machine learning algorithm on TensorFlow. Also, things we call it a wide model or shallow model. In some cases, because in logic regression, spatial logic regression, or LSVM, and basically with deep learning, you might want to combine those two things together. This is one example. Like we want to do some app recommendation. I want Chris. We want to recommend some app for him. What we can do for that? We can do some statistical counting, and then just memorize and to recommend some app. This is the traditional way we are doing this. And for this case, we want to deal with two things. One is memorization, and another is generalization. And for the memorization, we just many long tail features. And for the second, to make model generalize well. And in order to increase the model capacity, we can add some cross feature into a model. This is just a sparse logic regression model, as you can see. And we memorize something, and we also want to generalize something. But with you might want to increase more, and you want to come up with more and more feature class. And one thing is to do the factorization, and you have a different feature have different embedding, then to do the dot product between them, finally have the logics to predict the label. With that setup, very natural way, just use some more hidden. This is actually the deep learning, as you say. And we also have many sparse cross feature, and we already have. Let's drop them. No. We can just combine them together. This is wide and deep. It recently open sourced, and we also publish. And we set up basically used for combine the memorization with the generalization. Also, some good exploitation and exploration, and you have some good property on those model combination. And this is one typical architecture, and we have many. And the left part is just deep layer. We have multiple layer. We have embedding on it. And finally, we fit into a logistic. And the part is called the sparse feature class. We also have sparse feature class up. You can specify which 2 features, 3 features, or 4 features you want. You fit into that logistic log. And we left use sparse, we want some regularization, so you can use FTR optimizer, as I mentioned earlier. So with this, normally you can existing part, and we left with the deep add more hidden layers and come up with more feature to increase the model capacity. This is model architecture. And this is something interesting thing from TensorFlow community. Like DQN, this is reinforcement learning, and also like character INN and arrows, which is a wrapper touch together. We also open source by outside of Google, like Magic Trans and speech recognition system. Download and play with it. Yeah, this is pretty much all. Okay, we can answer some questions. Thank you.
Okay, any question?
What's the unique?
Yes. I think WinPack shared slides afterwards, right? Okay. Yes. Fine.
Okay, now it's on. Sorry.
I just want to know, is Apple do the similar things, or what's the difference? Maybe Google and Apple.
I think Apple is doing very similar things like deep learning. In the deep learning, we are exploring something like most popular one, sequence modeling, something like that. And you know about Siri, right? For Siri, you basically you need to do the speech recognition, and you need to understand what people want and what they are talking about. So you basically you still need to do the NLP. And I think a similar task just as Google. I think, as I know, Watson is use some more like a traditional technique instead of just deep learning. Okay, that's good. Yeah. Yeah, it's a huge system. Yeah, I do lots of things.
I have a question. So, yeah, I have a question here. Robin?
Yeah.
Okay. Now, my question is, how did you have a benchmark of your open source with other open source?
Yes. Yeah.
How does it look like?
Yeah, at the beginning, we open source last November. At the beginning, it was slower than the other framework like Touch or Cafe. After the 0.6 version we released a few months ago, and it has a comparable better performance like Touch. Touch is the best one, normally in open source community. So currently, in most task, benchmark task, TensorFlow performs as well as Touch or slightly better.
Like, I know Torch is pretty easy, you know, the first time for someone to just sit down, open it up, go through like some of the basic examples. Where do you see the strengths of TensorFlow versus Torch? Like, is it more on the ability I can have this thing running on a GPU here, that thing running on a GPU there, or about building different types of nets, types of architecture, strengths versus between the two?
I think yeah, same. They are general deep learning framework. So you can after flow this framework, you can build the different kinds of machine learning model. You say, in order to make user easy to use TensorFlow, we come up a few different tool or some interface, like we call it the TF-learn. TF-learn is a good example. You can just specify what's your input feature, how many hidden layers, and what's the size for each hidden layer, and what's the final problem. Is it regression problem or classification problem? So our thing is just need like 100 lines of code. You set up all your model. Basically, you don't need to deal with all the device like this GPU on this node or that GPU on that node. You don't need to deal with that. We have some very high level interface.
Following the question regarding IBM Watson and deep learning, can deep learning or TensorFlow do the same job as Watson does for Japanese? Can deep learning or TensorFlow do the same job as what Watson does for like Jeopardy, answer questions?
Oh, answer question. Oh, yeah, I got it. I think that's one of application above the TensorFlow. Not the TensorFlow itself can do this job, like deep QA, this kind of problem. So I think this is a very hot area right now, especially in some research community. And even inside of Google, we have many research are working on this problem above the TensorFlow. So yeah, the same thing. You can use TensorFlow to build your deep QA model and system.
Can you give beginners some tips on how to design a deep network architecture? For example, I start with a simple network. It doesn't work very well. Should I go deeper, wider, things like that?
Yeah. Yeah, that's a good question. I think there are some steps you can debug your model and basically make sure the model is doing well and doing expected. First of all, you need to check your loss. If loss is going down and down, it's fine. If loss a collation like this, then basically something is wrong. You need to figure it out. And TensorFlow has support some debug tool right now. And basically, like a very specific, you can print every node for the every value on it, just like a logging. And another thing is you check your gradient, make sure there are no some bad value on it, and yeah, something like that. And I think the visualizer TensorBoard is a good tool because you have the many summary. You can design some summary to report the status of your model, like log loss, AOC loss, like a gradient value, something like that. So
I have a question. One of the model, one of the slide you mentioned about GPU, is there, are all the GPU the same that we can use, or there is some GPU better than the other for using for TensorFlow?
Do you mean the different GPU in one system, right? Yeah, it's okay. It's totally okay. In TensorFlow, you can use the K20, K40, or something like that. You can use whatever because GPU they are compatible with the old version of it, so it's totally fine. You don't have to use just one version of GPU. Yeah. As far as I know, right now the GPU from NVIDIA, yeah, totally fine. But I'm not sure if AMD or some other GPU from other companies, if they are compatible with each other. I'm not very fully sure about that.
Example, that mid layer, is it like described some?
Middle layer?
Yeah, you know that.
You mean the attention layer? Or oh yeah, that one.
I would be interested.
Okay.
How it looks like. I mean, it's understandable.
Yeah, right now, because they are just some float value, high dimension float value. Basically, you can say we have encoder and decoder, so they are just output from all the encoder nodes. So each encoder you will output like 1,000 float node, and you unroll different. So you have like 10,000 floats.
Inside should be.
Yes, right, exactly. And you can do some projection into some 2D, and you can say maybe there are some words, if they are semantically close to each other, then in that 2D projection, they also close to each other.
Is that?
I think there are some other tools, not in TensorFlow, but it's very easy to use.
Give some reference.
Yes, sure.
Yeah, so it's amazing how far deep learning has come and how how much accuracy you can get with deep learning. Just wondering, with TensorFlow, because of parallelism, where do you think the architecture is going with unsupervised learning? So with supervised learning, you can get accurate results, but with unsupervised learning, you have a number of different factors. See the architecture much?
Right now, this is the very hot research area for the unsupervised learning, right? For the unsupervised learning, basically, at the intermediate stage, you can use the reinforcement learning or semi-supervised learning. And basically, you have some not huge label data, but you have the huge unlabeled data, right? Like this sequence model, you can predict, instead of the final label, you can predict the next step of the ID, like A, B, C, D. You can predict, at the first step, you predict B. At the second step, you predict C as something. That's to predict the next step. So this is, in this case, it's kind of semi-supervised learning. And also, like we talk about a little before, the reinforcement learning, right? You will not a final label, and you can use some reward and a penalty to guide the model to learn something. And for the pure unsupervised learning, honestly, I don't think there are much progress on this area. But I know, basically, some model doing very well, but they still have some label.
Good evening. Thank you for the lecture. Question, you talked about deep learning and how once you've trained the system to recognize dogs, you can perhaps use that to teach the system to recognize cats. So my question is really, how portable is the deep learning? Once you've taught a model how to play chess, can you use that deep learning to help you play Go? Or once you've taught a model to understand Putonghua, can you use that same model to understand Serbian or Hindi?
Yeah, I think that's a good question. It's kind of transfer learning. And something we are also exploring. And you basically, you have the image model and have some knowledge in it. Then you apply it into a different area or different task. Basically, they can share some knowledge between them. Like a translation, right? We can translation from language A to language B. But also, if you train some multilingual model without any label data, then model itself is able to recognize some language pair you never trained it before. So in some area, for learning is very promising. And yeah.
I'd like to follow up on that question. Has anybody done experimentation following up on the language translation concepts to be applied to linguistic families? Because, for an example, something that French and Spanish are all in the Latin family groups, and so they're going to have similar words and similar meanings, which makes them easier to understand. But if you want to take Chinese or Mandarin immediately, it's a completely different family root. So I was wondering if there's been any experimentation to apply this deep learning, once you've got it for multiple languages, try to merge the models into an understanding of family roots in linguistics.
Sorry, can you describe your question very shortly?
Okay, every language is derived from historic older language.
Yeah.
And if you follow the root back, you see that there's a combined language root. Like Sanskrit is the core of the Indo-European language model. And so if we're moving toward a universal translator,
yeah,
then in order to do that, we have to understand the parallelism between languages. And since we're working on this deep learning as a mechanism to build a model of understanding of the phonetic concepts and the terms, it occurred to me that it could be extrapolated one level beyond that to talk about how the languages are comparative in order to, and this would give us some very interesting information about the history of humankind.
Yeah, I think that's possible. And from our group, we haven't done any kind of linguistic experiment on it. And our current task is still something like a translation between different language pair. This kind of more application side. And yeah, but hopefully, well, there will be some progress on what you are talking about.
You
in future, yeah.
You also might want to think about merging with ontological work. When you look at the ontologies, because if you just think of the word stock in the English language, Google the word stock and you're going to find 20 different semantic definitions, different domains. And so that's another vector that we look at, is merging ontologies with deep learning.
Okay.
So I was wondering whether you can mention one or two good project for the beginner, and then if we master it, and one or two good project to become, when you become intermediate, familiarization with TensorFlow, because so that we can know that, hey, at least we know if we can do these two, we are pretty good, and we can move on to the second stage. So can you recommend one or two project for the beginner, and then one or two project for the intermediate TensorFlow learners? Thanks.
Yeah, in the TensorFlow website, we have lots of tutorial. In tutorial, we have different tasks, like image. You just need to do the classify for this 10 digits. And yeah, you can build a fully connected or convolutional neural network. It's very easy task for beginning to play with TensorFlow. And lately, you can, if you got more experience about TensorFlow, you can try some fuzzy model, like some language model. Or we also open source some translation code in TensorFlow. You can also try some translation, and you can very easily get data sets from WMT or some other data set, and to try sequence model, feed-forward model, and a convolution model, as I just mentioned. So I think there are lots of tasks in TensorFlow tutorial, and you can go through those tasks, and you will get more experience about TensorFlow. Yeah.
Okay, any more questions? Okay, thank you very much.
Okay, thank you.
Thank you, thank you. So next month, we'll have this topic, adversarial machine learning. So what I mean is this is going to apply for the natural language processing. So if you're interested, watch out for the meetup, or we'll send you the email. Since you already joined here, then we are going to form a group, and we'll probably send it out. And they'll be around the last week of September. So watch for your calendar, and there'll be good talk. It's going to be coming from the researcher from Stanford University. Okay, thank you very much for coming here. Hope to see you next time. By the way, we still have some pizza